left off yesterday with the direct comparison test, and we were looking at this series and trying to decide if it converged or diverged by direct comparison with a series that we already know. Well, there are only two series that we know. We know geometric and we know power series. We know P series. Which one does this most resemble? A P series, 1 over n squared. It looks a lot like that. Well, if I can find a P series that this is always less than or always greater than, that converges or diverges accordingly, then I can prove that it converges. So I do want to show that it converges. There's no question about what I'm trying to show here. So if I'm trying to show that it converges, then I need a sequence that is always greater than this sequence, right? That I know converges. Well, if I add 3 to the denominator, everyone agrees that actually makes it smaller. So 1 over n squared is always greater than 1 over n squared plus 3. Agreed? 1 over n squared converges by a P series test as n goes from 1 to infinity. So therefore, the series that we are looking at converges by direct comparison. It is less than 1 over n squared. 1 over n squared converges, so it must also converge by comparison. Any questions about that one? If we can use a direct comparison, it's a pretty easy test to use. The limit comparison is a little bit stronger and a little bit more difficult. Limit comparison will do more than just a direct comparison.
So for direct comparison, we can only do it if there's a formula that we already have memorized that's like it.
That's like it.
So like if we had like sine plus 3 or something, we could compare that. Maybe.
Right, you could compare that to sine.
Okay.
It would be greater than sine, and so sine, that would only work if you were trying to show divergence, because does that make sense? But yes, it's only if you already have know a sequence that converges. Mainly you're going to be talking about sequences that look like P series or sequences that look like geometric series. So this is a perfect example of one that would be a good direct comparison. If direct comparison won't work, then we will try limit comparison. This is probably the one that will come up the most often. Suppose you have a sub n greater than 0 and b sub n greater than 0. For all n greater than capital N, what that means is if the first 2 terms are negative, that's okay. If there's a place where after that all the terms are positive, then we can use a limit comparison test. If the limit of a sub n over b sub n equals a constant that is positive, then the sum of a sub n and the sum of b sub n behave the same. If the limit as n approaches infinity of a sub n over b sub n equals 0, and B sub n converges, then A sub n must also converge. Now, would you agree that if this limit equals 0, that means that at some point B sub n was bigger than A sub n? Right? Well, if B sub n is bigger than A sub n, and A sub n converges. Now, what's the difference in this one and the last one? Remember on the last one how B sub n and A sub n had to be bigger at every value along the way? This one doesn't have to be bigger everywhere. But it's saying overall the terms in the sequence as n approaches infinity is bigger. And so because of that, B sub n, if B sub n converges, then A sub n will also converge.
So basically, because they behave the same, it's saying because they eventually just kind of change and cancel each other out. So just
right. At some point, they start to, if the limit is n approaches infinity, if you ever get a constant, doesn't that mean the function on top and the function on bottom are very similar functions? Right? And so besides constants at the back, the Bill Gates principle, remember? And so they're going to behave the same because as n gets really big, they're starting to behave the same. Now, it doesn't mean their answer will be the same number, but it means if one converges, the other one's going to converge. If one diverges.
changes so close it doesn't.
Right. So if one converges, they both converge. If one diverges, they both diverge. If the limit is 0 and the bottom one converges, then the top one must also converge. Because, again, if this limit is 0, that's saying the bottom one was bigger. And if the bottom one's bigger and it converges, then the smaller one should also converge. Similarly, do you see the similarities between this and the direct comparison test? Similarly, if this limit goes to infinity, now what does that mean again? If the limit goes to infinity as n approaches infinity. Like think polynomials for a moment. When does that happen? The top was bigger. At some point the top took over and took you to infinity, right? So if the top is bigger and the bottom diverges, then the top would also have to diverge because it's bigger. This is very similar to what the direct comparison test says. However, the direct comparison test, you have to have something that is always bigger or always smaller, which is sometimes hard to find. So the limit comparison test is a stronger test. So let's look at example number 5. Lane and Kelsey. Okay, thank you. So let's look at this example. I want to determine if this converges or diverges. Right. What I need to do is find a function that is similar enough to it to compare it as a limit. In other words, it would be really good if the limit as this goes to infinity is the same as the function I choose. So if I look here, I get 3n over n squared. Does everyone agree? Okay, so that Joseph is picking a function that's similar by picking 3 over n. I'm even going to go to it with just 1 over n because it's very easy, right? Is 1 over n something that I can determine using a p-series test? Do I know that 1 over n is always greater or always less than that? No, and so I can't use just a direct comparison test. But I can use a limit comparison test. Because these two functions for a limit comparison test, because it's okay if the limit equals a constant, right? And I'm going to do that limit as n approaches infinity. So again, I have found a function with similar behavior. That's what I'm looking for. I'm looking for something that's kind of close. Doesn't have to be perfect, just kind of close. If I'm looking for a direct comparison test, I have to be perfect. For limit comparison, I just need to be close. If you had chosen 3 over n, it would also work. So if you had chosen that, it would work too. It's just a little more complicated. No. Before I keep working, before I keep working, let's talk about this really quick and how Joseph came up with the 1 over n. I'm again going to think about n going to infinity. The leading powers take over. Does everyone agree the 3n takes over on the top and the n squared takes over on the bottom? And 3n divided by n squared is just 3 over n. Does everyone see how he got that? Where that came from? Now, before I compare these, I need to know, does 1 over n, if my computer will work for me, does 1 over n converge or diverge to begin with? It does diverge. How do I know? Find out how I know that. Maybe it does. I don't know. What does it do? Does this converge or diverge? And what test are you going to look at? Remember, there's 2 tests for our comparisons, pretty much. What series is this? Is it geometric or is it p-series? That's really my question, right? Which one is it? Geometric or p-series? I suppose you could kind of think of it either way. P-series, probably the easiest. What's p, though? 1. Does everyone agree this is 1 over n to the first power? Does everyone agree? Okay, look at your p-series test. If p is 1, does it converge or diverge? Diverges. How do you know? By the p-series test. P is 1. If p is 1 or less, then a p-series diverges. So this diverges. So if this limit comes out to be a constant, then that would mean this also diverges. That's what I'm expecting to happen, but we'll find out. Okay? Let's do some simplification. How do you divide by a fraction? It would, because the bottom one diverges if your limit equals infinity. Three n squared plus 2n. If you need to pull L'Hopital's rule or anything like that, you are welcome to. In my opinion, I don't think you need that for this one. It's 3. That fits case 1, right? That's going to be our most useful case in the limit comparison test. So, they behave the same. Therefore, the sum is n equals 1 to infinity of, what was it? 3 plus 2, 3, no, it was 3n plus 2, wasn't it? 3n plus 2 over n plus 1 squared diverges limit comparison test. Now, if I hadn't shown my work, I'd need to say more, but they can see my work up here that I compared it with the p-series 1 over n. And I guess if you really wanted to cover your basis up here, you could say by p-series. So that one diverges by p-series. By limit comparison, this one also diverges. Any questions about that?
So, what is
A p-series is a sequence in the form 1 over n to the p power.
Okay.
And so,
that's just that we learned.
yeah, it was the second one. So there's two big ones that we learned that we can tell pretty easy, and that's geometric and p-series. So in our comparisons, often we will use one of those two as a geometric or a p-series. I am. I don't know why it won't stay up there today, but I am. For some reason, it's hiding today. Computers are strange. Some days it stays up there and you can see it all the time. I have something pushed different. I don't know if this is. Yeah, I don't really know. Okay, so let's look at some examples because we need to do some examples for a moment. And then we'll do some more tests. I don't know if we will finish today or not. We'll see. If not, it's not a big deal. We've got time. That's the beauty of this class compared to Cal 2 in college. We have time. Yeah, they start where they do power series only. And they talk about some convergence. They talk about some error bounds. And that's where they start. Then they go into Taylor. So they go more generic. And then they go back down to more power series and more testing. And it's kind of disjointed. And you can look at your textbook and see how it does it. That's how most people teach it. It's the way I learned it. And I got it eventually. But this is just much better because you get whole picture on all of them. Well, I'd never seen this till the summer. So the guy who did it this summer was just good, I guess. He's a... But they sent us to San Diego because they had some extra AP money. You get better people when you go to San Diego, probably. He's a table leader. He has written AP questions, and he is one of the people who, if the readers have a question, they go to him. So he's more than just an AP reader, which is already a big deal. But he writes questions both for the ABC exams and the statistics exam. So he's pretty... I mean, he did talk about the exam, but that stuff I knew. This was the most intriguing thing about that. Determine if this converges. What is my thought?
Looks kind of like a P-series.
Maybe.
Just kidding.
And this one's going to be a good one where we learn the difference between P-series and geometric. Where is the variable on a P-series? The n, right? The n's the variable. The p's just a number, like n squared, 1 over n squared, 1 over n cubed, 1 over n. This one, the n is in the exponent. Now, at first glance, it may not look like a geometric series, but maybe if we thought about that n being 1/2 to the n power, it does not look exactly like a geometric series, but I think we could compare it to 1 over 2 to the n. So even if you thought it was P-series, would everyone compare to 1 over 2 to the n? Does everyone agree with that? That seems like a good comparison. Whether it converges, whether it diverges, I don't know. But it seems like a good comparison to 1 over 2 to the n. We agree?
1 over 2 to the n be a full function.
Good question. If we can direct compare, that would be a good question, right? We can try. 1 over 2 to the n, Joseph said, is a floor function. Is that what you said? What does a floor function mean?
It means it's the lower of 2.
It's always less than, right? Okay. Now I need to figure out if this converges or diverges. If it diverges and it's a floor function, then I can say the other one diverges and be done, right? Good. This is really a geometric sequence. Does everyone agree with that? It's a strange way to write a geometric sequence, but it's really a geometric sequence. 1/2 is the common ratio. Does this converge or diverge? Converges. How do you know? Because 1/2 is between -1 and 1. So it converges by geometric series tests. So the direct comparison test is useless because it's not a floor or it's not a ceiling function, it's a floor function. So if the direct comparison test doesn't work, what do we go to? The limit comparison test. So it didn't work, direct comparison. Remember I told you direct comparison is a little more of a shot in the dark because you have to have a floor or you have to have a ceiling function. Limit comparison is a much better test. You will use it much more often because it's not as strong of requirements. So I'm going to do that limit. What should I do? Good. So I get the limit as n approaches infinity of 1 over 2 to the n minus 1 times 2 to the n. Any questions about that so far? As n approaches infinity, we all agree this -1 means nothing?
Yeah.
So 2 to the n over 2 to the n, that limit is 1. We've done 2 examples, and you're already really good at picking out comparison functions, aren't you? We've only done 2 examples. That's pretty good. Well, we'll keep trying. This one converges. The limit equals a constant. Therefore, what? Good. By limit comparison. Look at the next one. Is it hot in here? I have the air conditioner on, but up high. I think. That air not hot. No, I want it cold. I was trying to turn it on auto, and it won't stay on if it's on auto. Wait, if it gets cold, let me know. And I will go turn it back. Is it cold already? I could take my jacket off, so if it gets cold, let me know. Okay. I don't get hot very easy, so I don't get cold very easy. So when I was getting hot, I figured it was pretty warm in here. All right. There's no test, no immediate test, right? It's not a P-series, it's not geometric. I'm going to check that first. If it's one of those two, answer the question, be done, move on with life, and we're done. But it's not immediately either one of those. But can I think of one of those two things to compare it to? Does everyone agree that if I were to look at the limit as n approaches infinity, I would get 2 over n squared? So I'm going to compare it to 1 over n squared. You could choose 2 over n squared. 1 over n squared is just easy. Okay. So I'm going to use 1 over n squared. Do what? Right. Unless you can American Idol test it out, or P-series or geometric series test it out, we're going to try to compare it to a P-series or to a geometric series. And I'm going to choose 1 over n squared as my comparison. How did I choose that? I looked at the limit as n approaches infinity and tried to find a close match, because remember, I want the limit to be 1 so that I know that they behave the same. I could also settle for one that's greater or less than but then I have to think harder. So if I can find one that gives me the same limit on top and bottom, that's good. Good news. Before I start that limit, I'm going to side note and ask myself this question. Does this converge or diverge? If it were to the 1, it would diverge. It would, but it's to the 2. By what test? P-series. Have you noticed it's probably either a P-series or a geometric series that we're comparing to? So that one's a P-series. That one converges. If this limit is a constant, then the top one also converges. So if I picked a good comparison, then we'll have a convergent sequence. I think I did, but we will find out. How do you deal with fractions? Flip and multiply. So I get the limit as n approaches infinity. 2n cubed plus n squared. Again, if you come to one of these limits and have a hard time with the answer, don't forget about L'Hopital's rule. Again, on this one, I don't think we need L'Hopital's rule. 2. Sorry about that. Computer lag there. Does everyone agree with that? Therefore, what? Converges by limit comparison test.
So we don't have to tell where it converges at?
No, we don't. It didn't ask what the number is, and in fact, that would be a very difficult question on this one. The only way that we can find the actual number is on a geometric series, because of that formula we have from Algebra 2. So it's not calculus that even allows us to find that, it's Algebra 2. Although that formula came from calculus. Okay, another test. We are not going to finish the notes today. We are going to work for 5 more minutes. What that does mean is the homework is not due tomorrow. We still haven't done radius of convergence and intervals of convergence. So what I would rather you do some of the homework if you can, but then once you get to a stopping point, do worksheet number 1. You can do most of it, except for an error question that's on it. So do worksheet number 1 for homework tonight and pick around at this homework. But
the worksheet or the work pages in the book start with the grade.
Skip it, because there are some that ask, does this converge or diverge? So do those. You can answer the converge or diverge questions. But you cannot do the radius of convergence yet. Ratio test is the next test we're going to look at. We have one more test after this before we do intervals of convergence. No. It is. Is the limit as n approaches infinity of a to the n minus 1 divided, or a subscript n minus 1 divided by a subscript n equals L. There will be times when multiple tests will give you the same thing. So this problem I'm going to work, just because I'm about to work it with a ratio test doesn't mean that a limit comparison wouldn't work. There sometimes are multiple ways you can tell if it converges or diverges, but the next test we're going to learn is a ratio test. Probably won't get to example 8. Probably we'll finish writing ratio test down and do example 8 tomorrow. Again, go ahead and start those power series worksheets. Do a couple of those problems every night, and then when we finish this, we'll get the book open, whenever that may be. Yes, it will be the week before spring. Wait till tomorrow. I don't think we would have time.